Okay, so I think we are at lecture 37. So it looks like I'll do about 41 lectures. I think normally I would do 42 to 45 full semester, but anyway, I think this is good enough. All right, so as we discussed, the quantum Fourier transform is this, it's basically the quantum analog of the discrete Fourier transform. And it's a transformation. So we showed that it's a unitary transformation on an n-qubit space, right? So the idea is that you have some set of some orthonormal basis. Let me stick to the notation I used last class. Sorry. So by the way, this is all from chapter 5 of Nielsen and Chuang. So in Nielsen Chuang, they tend to first discuss Fourier transform and factoring and then move on to the search. I sort of flip the order around because I think that's a more natural thing to discuss after the Deutsch-Jozsa algorithm. Okay, so we discussed that this is a unitary transformation of this form. So if you have some orthonormal basis, which could be, for example, your computational basis, right? So the idea is this capital N is 2 to the n, right? So if I have an n-qubit space, the dimensionality is 2 to the n, and that's what we are denoting as capital N, okay? You're all hearing me and seeing the screen, right? If someone could just answer. Okay, good, yeah, all right. So now the transformation is to go from this J to a J tilde, which, as we discussed, is actually a different orthonormal basis. This also turns out to be an orthonormal basis, right? And this J tilde is nothing but a superposition of these J states weighted by appropriate phase factors. So this is 2 pi I jk by capital N get k, right? K goes from 0 to n minus 1. So this is the notation that I have. So we saw that an arbitrary state would transform as, so some arbitrary state psi, which is an n-qubit state, which has some set of coefficients like this, would go to some k is equal to 0 to n minus 1, yk get k tilde, right? And this transformation, actually, no, I don't want to say this in the tilde basis. I want to say that the J's get transformed to J tilde, which are superpositions of this form, right? So this is what I wanted to say. So this is again get K. So this is I'm just saying how an arbitrary state would transform under this QFT transformation, right? I hope you understand this. And this, when you do the QFT transformation, you end up changing these superposition coefficients xj to these coefficients yk, and the relation between these two vectors, right, where x is basically x1, x2, etc., x0 to xn minus 1. This now goes to the y vector, which is here, right? And you see that this transformation is nothing but the DFT transformation on these two complex n tuples, right? This is y0, y1, etc. So when you look at the coefficients, the complex coefficients, they form an n-dimensional complex vector, and those two complex vectors transform according to your classical discrete Fourier transform. The corresponding transformation on quantum states is the quantum Fourier transform, okay? And we showed last time, just simply using the properties of these roots of unity, that this is a unitary transformation. Okay, so now the aim of this and maybe part of the next lecture will be to work out the circuit for this quantum Fourier transform, right? So before doing that, now notice that, okay, so The rest of the lecture is going to be about getting a circuit for QFT, right? And somehow showing that this circuit does not have a exponential complexity with respect to the size of the system on which you want to do the QFT, but rather that it's actually a polynomial complexity. It's a polynomial scaling, right? And then that will show us that the quantum Fourier transform can be done exponentially more efficiently than the classical DFT, right? But before getting the circuit, yeah,
Ma'am,
yeah.
so this in place of K, we should have K tilde, right?
Here you're saying, right? No, the reason I put K is the following. So if you work through the steps, so maybe I can write down a couple of steps here. So you see this under QFT will become sum over j going from 0 to n minus 1 xj, and each j goes to j tilde, right? Where j tilde is now what? 1 over square root n, sum over k going from 0 to n minus 1. You see, I'm writing down j tilde also in the same basis.
Yeah. Okay. Okay. Yes, ma'am. Yeah.
And now this xj with this is what I'm calling now yk.
Hmm.
Do you understand?
Yeah.
So this
Yeah.
becomes some ykk, where the yk is now 1 over square root n, sum over j, j going from 0 to n minus 1, xj e to the 2 pi I j k by n. Do you understand?
Yes. So that means in this expression J and K both are belong to same basis, we can say.
J and K, yeah. This, yeah, if there's a
So
different basis, I put a tilde, right?
yeah.
So wait,
So
there's one more step before this. 1 second. So let me just write it like this. So this goes to, so each J, nothing happens to the coefficients, right? When you do the quantum Fourier transform, instead each J will go to J tilde. Then each J tilde, I'm expanding again in terms of the same basis, the K basis, because we've written the J tilde in terms of this basis. Do you understand?
yes. Yeah. So essentially, we are having a same state in linear combination. I mean, same state in same basis and two different linear combinations of the basis.
Correct. That's what the QFT has done. Yeah. The QFT has transformed. So the point is, you can either view it as a transformation of each basis state into a different state, which becomes a superposition of these basis states, right? Same thing results in a transformation of these superposition coefficients like this. That's the point of showing this. So on an arbitrary state, how do these coefficients transform, the xj and the yk? Do you understand? It's like saying that either the states transform like this, or for a given state, the superposition coefficients in this basis transform like this.
Yes. Okay.
Okay? Yeah.
Thank you.
Okay, good. Okay, so now before getting a circuit for this, note that the transformation is truly an n-qubit transform, right? Which means it looks like I have to send an n-qubit input. So I'll have an n-qubit input register, and then I have to have some box which is doing the QFT, and then I have an n-qubit state that comes out. And if I feed in as my input the computational basis states, then correspondingly I will get those superpositions. If I feed in an arbitrary state, I will get that transformation of the arbitrary state, etc. And so there's an n-qubit output register. Now, obviously, I can simply write down this unitary matrix in some basis and then use the techniques that we had shown about how you can decompose any arbitrary d-dimensional unitary in terms of two-level unitaries and so on, right? But now that may not be the most efficient way of doing it, and that's sort of not giving you a more general picture. The key thing now that we're going to do is to realize that this n-qubit transform can actually be broken down in some kind of product form. Okay, so the first step in realizing an efficient circuit for QFT is to realize that you can have a product form for QFT. So in order to do that, first, let's get into this binary representation. So as I said, n is 2 to the n, right? So let us represent this j, which as you know is some number between 0 and capital N minus 1. Let's represent this j. So you know that you can represent it as some, I'm not putting commas, as some n-bit binary string, right? So each ji is either 0 or 1. So this is an n-bit binary string that represents your number j, which lies between 0 to n minus 1. Okay. So now we don't just need j, but we actually, what we have here, if you look at these exponents here, you have things like j over capital N, k over capital N, etc. Right? So it will also be useful to note this decimal representation. So what do I mean by decimal representation? So if I write point j1, j2, actually let me write it like this. Let me write it as jl plus 1, etc. jn, say jm. Then this denotes, has anybody seen this kind of decimal binary representation? Somewhat standard in various applications. Anyway, the point is that this is now going to be, it's exactly like our standard decimal representation, where each decimal point becomes a inverse power of 10, right? So similarly, now each point is going to be an inverse power of 2, right? I mean, it's kind of oxymoronic to say binary decimal representation, but I think we're kind of used to this word decimal for representing this. So anyway, this is basically to represent fractions, right? So yeah, okay, good. I thought some of you in EE may have seen this. So this is, or at least in the EE courses that you take. So JL by 2, this becomes JL plus 1 by 2 squared, that is 4, all the way up to JM by what? 2 raised to m minus L plus 1. Do I want to say minus of L plus 1? Let's see how that works. So this is, for L it is 2, for L plus 1 it is 2 squared. So for m it is, yeah, I think this is fine, right? Yeah, I think this is fine. Okay, so this is what this point representation will mean, right? It's fractional powers of 2. Okay, and you will see that this is what becomes important when we try to break down that superposition into a product form. Okay, that's going to be the aim of the next few minutes. So this is the fractional powers of 2, right? Okay. So we are going to show, so let's show that this transformation, now remember kept j, I will write it as j1, j2, j3, etc. jn. Okay. Yeah, so note that for capital N, I'm saying 0 to capital N minus 1, but for this, I'm saying J1 to Jn, okay? Now, I may have deviated from the notation in the book, which probably uses 0 to little n minus 1, okay? And I hope you guys don't get confused, but yeah, this is what we're going to use, 1 to little n, okay? So the aim will be to show that after the QFT, instead of writing that big superposition of all these computational basis states, it turns out that we can actually write this in this following product form. So you can write it as 0 plus e to the 2 pi I point jn ket 1 in the face. Okay. So note that this is now a single qubit state. When I write this 0, this is a single qubit 0 and this is a single qubit 1. Okay. tensor, I'm explicitly writing the tensor just to make it clear that these are all single qubit states now. So the next phase now involves two of these J bits, okay, and so on and so forth until the last single qubit state involves all n of them, right? So this is J1, J2, etc., Jn, get 1, right? And of course, there's an overall normalization of 2 to the n. For every single qubit state, you can imagine there is a 1 over, there are n of them, right? So 1 over 2, right? For every single qubit state. Okay. So we are going to show that after the QFT, the state that you get, while originally we had visualized it simply as a superposition of these computational states with appropriate phase factors, can now be written in this product form. So this will then help us to identify what are the gates that we need to apply qubit by qubit, rather than taking some big 2 to the n cross 2 to the n unitary matrix and having to then decompose it into single qubit and C naughts and so on. Right? This then will give us an elegant circuit description of QFT. But the first order of business is to show that this is indeed possible. I'm sorry, yeah, this is 2 to the n by 2, sorry. Yeah, it is basically square root n, remember? I'm wondering why is there a 2 for everything? Each one should have a factor of 1 over root 2, right? Sorry, this was my mistake. So yeah, the denominator should be square root of 2 to the n. So for every qubit, you have a 1 over square root 2. And if you recall, for the single qubit case, now it will be clear, right? The single qubit Fourier transform we discussed last time is nothing but the Hadamard. So if you ignore the rest of these things, starting from here on, if you ignore the rest, then what you have basically is just 2 pi I. Jn now, well, it depends on which way you want to look at it, J1 or Jn, but it doesn't matter. It will either be 0 or 1, right? And if it is 0, there is no phase, and I mean no non-trivial phase. And if it is 1, then it just becomes a minus sign for the first qubit, and that's it, right? So the single qubit Fourier transform is simply the Hadamard, can be seen easily if you look at this breakdown. Okay. Okay, so let's just work our way towards this just to convince ourselves that this is the case, because this is the key step. And then, you know, the circuit kind of naturally follows from this. So remember that J now has to go to, this is how we wrote it first, right? We have to show that this superposition breaks down into this. So now K going from 0 to capital N minus 1 is nothing but 2 to the N minus 1. E to the 2 pi I j k by 2 to the n k, right? So this becomes, so now note that you can write this as, so I'll write this right here, k going from 0 to 2 to the n minus 1 jk by 2 to the n. So this can now be written as k1, k2, etc., kn, right? This is another n bit string, this k, correct? Okay, so now this I can write as a, so now when I write this n bit string, so I hope this idea is clear, that when I write this n bit string, this is nothing but J1 tensor J2 tensor etc. tensor Jn, right? That's what I mean when I write this. So if you imagine a 2-bit string, then I will write strings like 0, 0, 0, 1, 1, 0, 1, 1, which is nothing but 0 tensor 1, 0 tensor 0, 1 tensor 0, 1 tensor 1, right? So this also similarly then becomes, this is nothing but k1 tensor k2 tensor k3 etc. kn. So now you see we can break down this sum over 0 to 2 to the n minus 1 into sums of k1, k2, k3, kn, etc. This is basically a sum over all the n qubit states, right? So all the n bit strings, which means each ki must sum over 0 and 1. That's all, right? Okay, so this becomes sum over k1 going from 0 to 1, k2 0 to 1, all the way up to kn 0 to 1. Capital N is 2 to the n, of course, right? So then I'll write this as k1, k2, etc. kn. So now the game is to consider, so if I want to now break down this sum, right, it is still a sum over all the n bits, and what is sitting here is a tensor product. But if I now want to pull out each ki somehow and make it into a product form, then I must look at where are the exponents where those ki's matter, or where those ki's figure, right? So what we will do now is to represent this k on top, right, as in that point form, right? Because this is basically of the form k over 2 to the n, but then k is nothing but k1, k2, k3, etc. It's that string by 2 to the n. So then we can represent this in this form. So let me just say that. Yeah, so let me just write one more step and then do the breakdown. So I will have k1, k2, etc., kn. So this k over 2 to the n, I'm going to write it as sum over L going from 1 to n, KL 2 to the minus L. Okay, this is in the exponent. And then I have K1, K2, etc. K. So why is this the case? Because recall that K will be written as so the idea is that I can normally write K as sum over L going from 1 to n, KL 2 to the n minus L. Is this clear first? Maybe I should have written this up front here itself when I wrote down this binary form for J. So when I write this binary form, it also means, so this is, okay, this is not an equal to, maybe it's an equivalence, that this is the binary representation. But if I want to really write down what the relation is between each Ji and this J, then this is going to be sum over some L going from 1 to n, JL 2 to the n minus L. Is that clear? Because you have the most significant and least significant bit here, right? So L is 1 is what? It is J1 2 to the n minus 1, right? Whereas the last bit, which is Jn sitting here, that will be the 2 to the 0. That will be the bit that accompanies 2 to the 0. Then Jn minus 1 is the bit that will accompany 2 to the 1, etc., etc. Right? So I hope have this in mind first, okay, when we say that this is the binary representation. So this, we use this for k here, right? Then when you do k over 2 to the n, this simply becomes sum over L going from 1 to n, KL 2 to the minus L. Okay, so that is what I have written here. So k over 2 to the n has been written like that. Now I just want to, so let's keep these sums aside and let's just look at this part. you see I have the sum over the KLs in the exponent now. So the natural thing to do is to take out this sum in the exponent and make it into a product, right? And then you can associate, therefore, naturally each KI with the corresponding get KI here. Is that idea clear? So that will be the crucial step. Since I have written the exponent like this as a sum in powers of 2, rather fractional powers of 2. So then this will become, this is what leads to this step. So now from here we come here. So I'm going to write this as a product over L, right? L going from 1 to n, e to the 2 pi I j kl by 2 to the L, right? Get kl. And actually, instead of this product, what I should be writing out here is what's called a tensor product, like this. Because I'm now breaking up, so maybe I can write just one more step here. So this comes here. Let me just write one more intermediate step here. So this part alone becomes e to the 2 pi ij. So it's k1 by 2, get k1. Then I can write this as tensor 2 pi ij k2, oops, by 2 squared, get k2, etc., etc. 2 pi I kn by 2 to the n, get kn, right? That's what this becomes, right? There is a sum, forget all the sum over these k's. This is not what I'm talking about. So keep these aside. This is what will finally give us the 0, 1, 0, 1 superposition for every qubit. This sum over ki's. What I'm talking about is just this part. That you have this sum in the exponent, that obviously becomes product of exponents, but each such phase is now associated with a particular get ki, right? And so basically I can write this in this tensor product form. Okay, and so this is what I have written here. Hope that is clear. So now there's nothing much left to do, right? For every tensor product now there is a sum like this, right? Where each ki goes from is either 0 or 1, right? So now if k1 is 0, so every time a particular ki is 0, what happens? This phase factor vanishes, correct? So every time a certain ki is 0, so look at kl, for example, which is the lth term here, the lth term in the tensor product. If kl is 0, this is ket 0, and the phase is, there's no phase. If kl is 1, the phase is j over 2 to the n. Is that clear? Okay, so let me write it like this now. Oops. So I have now tensor product over L going from 1 to n. For each KL, I'm now taking this, using the fact that each KL is either going to be 0 or 1, and there is a sum over that. There's a superposition over that, right? So this will be 0 plus e to the 2 pi I j over 2L. Get 1. So the last step is simply expanding this tensor product, right, from 1 to n. And when L is 1, then this is just j over 2. And when you have j over 2, you can again expand the j as a sum over its binary representation coefficients, right, in powers of 2. You once again expand j in powers of 2, and then you divide that by 2 to the n. And that is what will give you this point representation that I had here. right? So in a sense, with this we are done, right? Because this has already given us a product form. Correct? All that the last step is doing is to once again expand the J as a binary sum, is realize that J is nothing but, now I'm going to write some M or something, going from 0 to, oops, all of these are 1 to N for me. Then there is a Jm 2 to the N minus M, right? So you use this and then you plug it in there, right? And then you can write down what it is when L is 1, it's J over 2, which means what happens out here, you end up with a sum over M going from 1 to N, you will have Jm over 2, right? So anyway, let me just expand that out. So let me say that this now can again be written as so this was my J tilde, right? So remember we started with J and the QFT takes you to J tilde, which is then now becomes this, it became this tensor product, L going from 1 to N, 0 plus e to the 2 pi I j over 2 to the L, 1, right? Of course, overall there is a 2 to the N by 2. So the last step is to break this down, and this then breaks down as follows. So you have the 1 over 2 to the N by 2. And when L is 1, this becomes 0 plus 2 pi I j over 2, get 1. So j over 2 squared. Okay. And then the last step is to simply use again the binary expansion of J to show that this is what you now have. Will become Jn minus 1 Jn. This now has J1 to Jn. Yeah. Okay, so this kind of shows this product form. I think is this idea clear? It's just the last step maybe where you may want some further explanation. So remember that this is the binary form, right? Now I'm dividing this by 2. Dividing this by various powers of 2 in the exponent, right? So yeah, sorry, I was just wondering whether I swapped the order of the qubits somehow. I don't think so, but Anyway, let's see. So this by 2 and then a sum over m going from 1 to n is what this will be. So you will notice, so do people understand why this became this? So I said, I gave you this hint that this comes from this sum, but beyond that, what? So I have a sum over jm 2 to the n minus m, and then there is a by 2, right? So what you should notice is that whenever I have, if I do not have a fractional power of 2 in the phase, right, then that phase is non-trivial. I mean, sorry, trivial, right? So when I say e to the 2 pi, oops. So let me do the first one for you. So I have e to the 2 pi I j by 2, right? That becomes e to the 2 pi I sum over m going from 1 to n, jm 2 to the n minus m by 2, right? The question is, which of these bits in the jm binary representation is really going to contribute a phase, right? And I hope you will see that it is jn alone that contributes the phase. So let me say this: j1 2 to the n minus 2, j2 2 to the n minus 3, etc., all the way up to jn. Now what happens with jn? It is no longer a power of 2, it's just jn by 2. I'm just expanding this exponent out, right? And now I hope you will see that everything all the way up to here is all trivial, right? E to the 2 pi I times something, right? Some power of 2, correct? And so the only non-trivial part of this phase will be jn by 2, which is what we are calling e to the 2 pi I point jn. Okay, so I hope this idea is clear. And so using this, you should be able to work out each of these phases. So in the second case, what do I have? I have a 1 over 2 squared. So then there will be 2 bits of j that will contribute to the phase. All the other bits will simply have powers of 2 in the numerator. I mean powers of 2 times 2 pi I, which will all vanish, and then there will only be 2 of them which will have fractional powers of 2, which will contribute some non-trivial phase, right? Because it's only when I have jn by 2, and then in particular that jn bit should be what? If it is 0, again there is no phase. If it is 1, then I have a pi by 2, e to the I pi by 2. And that is when I have basically the Hadamard gate, right? Similarly here, I will, depending on whether jn and jn minus 1 are both 0, or one of them is 0, or both 1, I will have some non-trivial phase here. The rest of the bits will not contribute because they will all accompany some power of 2 here with 2 pi. Okay, it's only when I have fractional powers of 2 will the bits contribute to some non-trivial phase. In the very last one, I have e to the 2 pi I j by 2 to the n, right? Because this is L going from 1 to n. Remember this tensor product. So the last one has j by 2 to the n. Then you realize that all the phases, all the bits will contribute to the phase, right? Because the expansion is power of 2 to the n minus m, right? So the largest power is 2 to the n minus 1. So from the first bit onwards, like I don't know, whichever you call the most significant or the least significant bit, but all the bits will contribute. J1 through Jn will contribute for as far as this phase is concerned. Okay. So that is how we end up with this product form. Is the idea clear? It's just a matter of, so there was nothing very complex about this product form. It's just that noticing that the QFT has this product form becomes a very important step, right? And the observation is sort of not very, it's not nothing very technically deep or analytically complex. It is simply playing around with this binary form, right? So what did we do? We noticed that these Ks are nothing but, each bit string, each computational basis state is a product, is basically a tensor product of this form. Then it was a matter of recognizing these phases, right? This is where it looked like, it was not going to be a product form because I have this sum over all the Ks and the G, all the Ks. So that now can be, once you realize again, break it down in its binary representation or in powers of 2, then you realize that only certain powers will contribute, right? So then you realize that each, this exponent breaks down into a sum over the Ki's. And then I can therefore make it into a product. That's all. So once the exponent factors into a sum over the Ki's, then it becomes a product. Some of you have done statistical mechanics will have, I don't know whether you've done partition functions and things like that, but you will notice a similar thing play out there. Like when you go for an n particle function, when you have n quantum particles and you're trying to write down partition functions, then I don't know if you guys have done bosonic, fermionic partition functions and things like that. So there you will again notice something like this play out. You expand it in some appropriate basis, like occupation numbers or something. And then you will notice that the partition function, which is like, you have a sum over energies and so on, that again will break down like this. So this is the key step, that this exponent becomes a sum, which can then be written as a product, and that product can be then made into a fact, essentially implies that this part becomes a tensor product. Then all that remains is to sum over each Ki value of 0 and 1. So in each tensor product, you notice that there is a superposition of this form. And like I said, that's it. This is the product form. Now you're further simplifying it further by realizing that this J can be written as a sum of powers of 2 like this. And then that gives you this form. This basically tells you which are the bits of J which contribute for each phase. Why is that important? Because now I'm going to draw the circuit based on this. So when I draw this circuit and I have these n input qubits and then n output qubits, the first qubit state you will notice at the output, when I say first, I mean this, let's say, right? This depends only on Jn. Now, what is Jn? Jn is actually the last qubit here. So if I were to write, input this n qubit state here, right? Then this is how I'm going to input the n qubit state. Then you will notice that the first one here actually depends on this Jn, because this is actually what? 0 plus e to the 2 pi I Jn by 2. That's what matters, right? Ket 1. So if Jn is 0, this is going to be 0 plus 1 by root 2. If Jn is 1, this is going to be 0 minus 1 by root 2. Right? I hope you see that. I'm sorry, I said pi by 2. No, I should have said pi. The first non-trivial phase is pi. Yeah, okay. So similarly, you notice that the second qubit now, so I don't want to draw the circuit now in the last 5 minutes. So I'm just giving you the intuition for the circuit now. Okay. So this is the second output qubit. And you notice that the second output qubit, what does it depend on? Are people still around?
n minus 1.
Correct. It depends on Jn and Jn minus 1. So good. So I suppose the idea is clear. So this has some phase which depends on Jn and Jn minus 1. So Jn minus 1 is sitting here. And so on and so forth. And then you see that the last qubit here actually depends on all the n qubits, meaning whether they are all 0 or 1. So when I write the n qubit state, the question is whether each Ji is 0 or 1. right? So this now depends on all of them from J1 through Jn, right? Okay, so you notice therefore that there is a kind of swap happening, right? So somehow I have to condition, I have to condition this state on this one. I have to condition this state on these two. I have to condition this state on the 3 from the bottom, right? And this one has to be conditioned on all of them. So the circuit will basically be comprised of Hadamard's and rotation gates, right? And maybe I'll just quickly show you what it looks like or not. I mean, it's going to take me a while to just draw the circuit. So let me do that at the beginning of next class. But because of the way this conditioning is happening, in a kind of inverted way, you will find that what we will end up doing is, you see, this one is conditioned on all the n qubits, right? So we'll actually end up swapping the qubits at the output. So we will actually realize the circuit in the in the kind of inverse order, where we'll have the first qubit depending on all the n qubits, the second qubit depending on the last n minus 1 qubits, the third qubit depending on, and so on and so forth. And then in the end, we will do a bunch of swap gates. Okay, so you will find that that's what the circuit looks like. And maybe I'll just draw the circuit at the beginning of next class and explain it. Okay. So I think maybe let me stop here. I don't want to go beyond time too much. So I see that I have about 20 of you here. So I hope the 25th November works for everyone. Someone had an exam on the 22nd, which is a K slot. So I can't hold it on the 22nd. So I'm holding it at the M slot, which is 25th November. And I hope everyone is okay with that. Okay, so next class we'll draw this circuit, and then we will see a simple application of this, which is in phase estimation. I hope this idea of the QFT is clear, how to break it down into a product, and how to and which, how to see the conditioning on which qubit is conditioned on which input. Okay. All right, no further questions. Then we'll meet on Monday. Okay, see you all on Monday.